All right, we're going to take a look at problem 7, which is a truck is driven at constant speed down the street. So first of all, we're going to choose our system. So pretty clearly, I want to use the truck as my system. All right, and then you say, well, we have to decide what else we want to include. And so we usually take a look at what external forces are acting on the system. So if I did a force diagram for that truck, like what else would show up on the diagram? Like, well, ranged forces is going to be gravitational force. Okay, contact forces, what's touching the truck? You're like, well, the only thing touching the truck is the ground, right? And so you say, well, are we being pressed together? Yes, then there's a normal force up on the truck by the ground. Then you ask, hey, are those surfaces trying to slide past each other? And you say, well, at the tires, right? Okay, at the tires, we know that the way that a car drives itself down the road is they go ahead and the tires are rotating. And at the bottom surface, it's like the tire is trying to slip backwards, right? And you say, but friction fights against it, static friction, and drives the tire forward. Okay, is the way it works. It tries to slip back. Static friction says no, 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 and pushes it forward. Is the way it works. Assuming that we're rolling along, without slipping or sliding, which is what happens when a truck goes down the road. Those tires aren't sliding at all. It's static friction. So I'm just going to represent that with a static friction force there. And so in this problem, then you'd say, hey, that would be it, right? Hey, if I look at that force diagram, you say, wait a minute. My total force here, I can see that the vertical forces, I can imagine those would balance out, dunk, 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 and so I wouldn't accelerate up and down. But you say, if I'm driving myself forward, I would need a force against that to balance it out if I'm going to go at constant speed. And we know this truck's going at constant speed. What is it that I have to fight against here to balance out and to drive this car forward? So what we're going to have to consider here actually is something that we've pretty much in this course said that we're not going to need to worry about usually, and that's air resistance. The air resistance is going to be significant on a truck rolling down the road with that big front, especially if it's going on the highway. And so I will need to balance out that force with an air resistance force. As we're slamming into those air molecules, shoving on them, they would push back on the truck. And I would have an air resistance force. Now, I usually label that as like a F resistive, little r for resistive force, pushing against it. And if we're going at constant speed, those are going to balance so that we go at constant speed down the road. So the question now is, now I can see what else is interacting with the truck. I might consider expanding my system if I don't have to have a work term, right? If I don't want to have a work term. What else might I want to include? Well, I might include, well, you say, is there going to be energy transferred between the truck and the road? And you say, well, that static friction, it's not really like pushing through a distance per se. Or is it? Doing work on that truck. You say that resistive force of the air looks like it's taking energy out of the system, though, for sure, pushing against the motion as we're driving along, and that air resistance force. As we push on the air, we're going to make the air molecules swirl around more. We're going to give those molecules more random motion, more thermal energy, for sure. So let's take a look at this, right? So as I take a look at this, let's run through now. At this point, you say, let's try. This time, I think I'm going to try doing this diagram with just the truck as the system. Okay, we can talk about expanding the system to include other things if we would like. But for now, let's try this one doing just the truck. Just the truck. Now, as you run through, we think about what different types of energy we're going to consider. And so you say, well, only the ones that are changing, right? So let's run through our list. So we talk about maybe kinetic energy. Is the kinetic energy changing this problem? And you say, well, kinetic energy has to do with it's proportional to mass and the speed squared. We're going at constant speed. You say, are we changing the mass of the truck significantly? Probably not. And so we would consider that kinetic energy to be constant. And so do we need to consider it? No. If it's constant, we don't need to analyze it. So then you say, what about gravitational potential energy? You say gravitational potential energy is proportional to mass, field strength, gravitational field strength, and the height. You see, we're not changing any of those. So that's constant, so we don't need to analyze that. Then we go to elastic potential energy. Do we have some material that's elastic that we can stretch and then it'll want to return back to its original length, or compress, it'll want to return back to its original shape? And you say, well, no, we're not really doing that here. It's true the tires are compressed some, but those tires, they're always at the same amount of compression. I know that as it rolls around, one part might be compressed, but then the next part's compressed, the next part's compressed. It's always overall the same amount of crush going on in that tire. And so that elastic energy in the tire is staying constant. And so I don't need to consider that. So I don't have to consider elastic potential energy. So what next? Chemical potential energy. Do we have a chemical reaction going on? And this is where you say, yeah, there is. You say, what's the chemical reaction going on in the truck? You say, well, that's happening in the engine of the truck, right? We're converting oxygen from the air and fuel from the gas tank, and we're combining them to create carbon dioxide and water vapor and heat, right? That we're using to drive the engine. And so you say, so yeah, as we go ahead, we have a chemical reaction going on. And so the energy we have in that fuel and that oxygen to start with, compared to the energy we have, that chemical potential energy in the arrangement of the molecules of the carbon dioxide and the water vapor at the end, those energies are not the same. There is less potential energy in carbon dioxide and water vapor than there was in the fuel and the oxygen. And so we are losing chemical potential energy. By losing, I mean it's decreasing chemical potential energy. It's not being lost from the universe. It's just converting into thermal energy. And as the gas and the pistons of the car expand and the truck expand, they're going to then push on pushing the pistons, which pushes the drive rod, basically eventually turns the axles and turns the wheels and makes the car go. And so we are converting energy from chemical potential into thermal, into that kinetic energy of the motor and the wheels, and pushing the car down the road. So we're using up that fuel, right? We're converting it from fuel and oxygen into carbon dioxide and water vapor. And so we are changing the total amount of chemical potential energy stored up in the fuel in the tank of the truck. And so we need to consider chemical potential energy. All right. What else is going on? You say, last one is thermal. You say, we know that we are generating a significant amount of thermal energy. Now, some of it's being converted into moving the parts of the engine. But if we're going at constant speed, those parts of the engine are generally, those parts going at the same speed all the way through. So we achieve the parts. And so that thermal energy, though, is where that is going. All right? Overall, you'd say, I know that like a car's engine is cold when it starts, but it heats up. But as I go along, some of that thermal energy is then being transmitted into the environment, right? Radiating out into the environment through. It's also going into the air around the truck. And so once you're driving along, basically the temperature stays. It's warmer, but it stays relatively the same as you drive along. And so I'm not worrying about like the temperature rising in the truck over time or anything. But thermal energy is going to be leaving the truck. And so I guess if my system is just the truck, is the temperature of the truck changing over time, right? You see, I know at first when I first started up, but once I'm moving along, that truck engine stays at pretty much the same temperature, right? The truck stays at pretty much the same temperature as it goes along. You say that thermal energy, though, it is radiating out into the environment. I'm pushing on the air and making it swirl around more, giving the air more thermal energy, and some heat's radiating out and stuff. So actually, I take it back. The thermal energy of the truck is staying the same. I'm just losing chemical potential energy. And where's it going? It's leaving the system, right? Okay. That air resistance force pushing against me, taking energy out of the system. This is work done by that resistive force, right? Taking energy out. I have some chemical potential energy at the start, and as I use up that gas, I'm getting less and less in gas in the tank, less and less chemical potential energy stored up. We can pick a value to start with. We don't have any zeros here. We're not driving this truck until it runs out of gas in the situation. We're just looking at it as it rolls along. Maybe I have, I don't know, 12 units of chemical potential energy, and as I drive along, I'll have less and less stored up in the tank. Going from the start to the end here, I started with 12 and ended with 8, so I've lost 4 units that left as work done by that resistive force of air resistance pushing against me. If I could take away, it sounds weird, I still need oxygen, of course, to combust the fuel, but if I took away that air resistance force somehow, then this would drive my truck faster and faster and faster. And these 4 units would go into kinetic energy, and it'd be going faster and faster. But that air resistance force pushing against me is enough to keep me going at constant speed, right? If I didn't have any air resistance force, right, then would I need to keep running the motor to keep myself going at constant speed? If I didn't have the resistive force, I could just roll along. Now, because we've already talked about the fact that there is also a little thermal energy generated in the flexing of the tire, right? The parts of the tire having to slide past each other as we change shape and deform the tire. And so it would not roll forever. Also, the ground under the tires would deform, right? As the tire presses down on the ground, it would deform the ground, right? And so there'd be deformation there too, and work done to change the shape of the ground there. So the point is, but if I ignore those little bits of heating there, you say largely it's the air resistance slowing it down, I think, at highway speeds, are trying to slow it down, that we're having to push against and expend energy to maintain our kinetic energy. But yeah, against that external force. But yeah, that's the short view of problem 7, I think. Yeah. If I want to expand my system, let's do this in an alternate way. What if we expanded our system and we decided to include the ground in the air, right? Essentially everything. Well, now this force from the air is no longer an external force. So that would go away from the diagram, right? That thermal energy doesn't have anywhere else to go. It's in the system. It's going to be staying in this whole system. It's going to be heating the air and the ground from the truck goes by. But now it's inside our system. So actually, we'll have to consider thermal now, because that will be changing. The truck isn't getting hotter, but the air is, and the ground is as it rolls over it. And so I'll have this, maybe we'll choose to call the starting energy 0, thermal energy 0. And now as I go along, energy is not leaving the system, so the total has to stay the same. So if it was 12 here, the total here has to also be 12. So I'd have 2 in thermal. Total here has to be 12. So now I'll have 4 in thermal, right? And that's what it would look like if I used the entire, if I expanded my system to include the ground and the air. So, yep. So that's what those are my thoughts on the last problem, problem 7, from worksheet 1.